Okay, here we go.
Here we add a glass plate. This is a window pane glass between the mask and the screen with no change to the pattern. Now we want to look at an older experiment done in 2015 where we place an opaque mask with a single slit between the first mask and the screen. Now the second mask is positioned such that the central peak from the first mask falls across the slit, and we end up with a diffraction pattern on the screen. Next, we make a change to that second mask, and then we take two pieces of glass, put them such that there is a slit of approximately a half a millimeter between them. And what we get is interference fringes, as you can see here. This is different, of course. The next step is to place a nail, which is an opaque mask, between the first and second mask, such that the light is blocked that would normally go through the slit. And now there's a trick to this. The trick is we don't place the nail such that there's light from both sides of the nail, because then you would get diffraction patterns behind the nail. Instead, we place the nail so that the edge of the nail appears to be at the minima of the first slit diffraction pattern. Then we get no light behind the nail. But however, you'll note that in the end, the interference pattern is roughly the same. Therefore, the nail is not causing the interference pattern. It's the slit that's causing the interference pattern, but there's no light going through the slit. The model that we suggest is that corpuscles are the smallest minimum mass in our universe, and that a photon is a column of these corpuscles. Here you see the column. The energy of the photon is the number of corpuscles in the photon. As the photon moves, each of the corpuscles generates waves in the ether. The mass for this is the same as for the linear array of dipole antennas. And this is the effect on the ether, in that it causes these peaks and valleys in the ether, which is then going to be directing the photon. So here we have a photon, and here's the mask with atoms in the mask and no atoms where the slit is, and here we have a screen. The photon emits gravitational waves, which are then reflected from the atoms and not reflected from the slit area. And when you do the math for this, you end up directing the photon according to the Fraunhofer diffraction pattern. Here we track individual photons in the computer simulation. You'll see that they begin by starting to change direction toward the mask. This has been observed by some observers. The second thing you'll notice is that the area near the edges of the slit appear to be brighter than in the center of the slit. This also has been noted by observers. What has not been noted is that the photons from the upper edge of the slit are directed towards the bottom edge of the screen, and vice versa. In the simulation, calculate bins and then count the number of photons that arrive on the screen in each individual bin, then of course print it out. This then is the number of photons in that bin. The solid line is the Fraunhofer diffraction pattern calculation. And you can see that the calculation and the bin structure is very, very close. It's a good simulation. Here's the same thing for a double slit. And you can see the interference fringes here. This is a simulation of the C structure that we mentioned before. The bins are large here, so we kind of mush out any of the details. But you can see there's an indication there might be fringes here. And here we make the bins smaller so that we can see detail. There's an interference fringe. There's another interference fringe, and a third. This is the simulation of the D experimental setup. You'll note no photons going through the center of the screen, which is the nail doing the blocking, and that there is an indication of interference fringes, just like in the C simulation. And the outer reaches look the same as with the C. Now, the Afshar experiment places wires at the minima of interference fringes, and then it claims, Afshar claims, that he can then determine which slit the photon came through, which is contrary to the Copenhagen kind of thinking. The Copenhagen thinking then said that, well, the wires must be collapsing the wave function. Now, the current experiment would argue with that because the C and the D versions look the same, and therefore the nail was not causing any issue. In the Afshar experiment, we repeat that with a simulation where we keep track of the angle each photon was going when it hit the screen, and here you see the plot of that versus the screen dimension for one slit and versus the other slit. We can keep track of the slits, of course, because it's a simulation. And when you apply a linear regression to those values, you find that one slit is directing the photons in the negative direction, the other in the positive direction, thus achieving a separation of the slits, which is exactly what Afshar claims.
Well, that's it. We're off now, right? Or
I think Christopher, your mic is off.
Yeah, we can still see your screen if you want to stop sharing it. Because otherwise we're kind of looking at clones of ourselves that are brilliant.
there, we're now okay, right?
Okay, yeah.
No, I can still see.
You have to do the X on the box. You have to press the X on the box.
Yeah.
I gotta turn on the video. I guess,
yeah. And then X on the square box next to the mic. You have to X.
Oh,
you have to press on that.
Sharing. Okay, right.
Yeah.
Now we turn on the video.
Now you press on that, it'll stop sharing.
Turn the camera on.
You have to put your camera on, video.
Is your video working? It looks.
You can.
It looks.
This is another thing. This is my camera. See.
Yeah, it should be coming on.
But I wanted to show you as an expansion of that, of what the what the simulation is. And I don't know if you can see that. Can you expand that out to?
How about that?
Can you expand that out?
I've done my best. Is everybody able to see it now?
Not. Maybe you can zoom. Is there a zoom function?
I think it needs to be focused a bit. It looks a bit blurry. Or maybe if you can up the resolution or the focus. But size.
No, it's because it's small here. This is very small.
Oh. Oh, well, no, it's coming into focus a bit, as if the resolution, I think it's really a bandwidth issue. So give it time, it might resolve itself.
No, I can't do that.
Oh, yeah. Oh, no, yeah, it looks like it maybe I don't know if you can get it a bit closer, maybe.
Well, yeah, but it's coming out very small, and I tried to get it closer there.
Yeah, that's closer. It's still a bit blurry, though, for some reason. There's probably an optimal distance where things come into focus.
Well, this is a textbook page, and this is how you do a linear array right there. And what you get down here is essentially a Fraunhofer equation. I mean, this is the simulation. This is how we do the simulation. Right? It's the math of the simulation.
Very cool.
So when you run that, you get that kind of graph, if you remember it from the video.
Yeah.
Where this is eagle up here, and that's your bin count. Now, here's doing it again, only it's this way.
Yeah.
See? Now, you should find some familiarity with this, because this is your Mexican hat, isn't it?
Oh, yeah. I know what you mean, yeah, because I have a Mexican hat thing as well that works off the Higgs field, and but it has multiple fringes on the edges.
Yeah, right here.
Yeah.
And here and there. All right. But the question is what is this axis here? See, here we're going negative.
Uh-huh. Yeah, okay.
And that's the problem, is you go negative in that, and that would imply there's negative mass.
Okay.
But to correlate with your, let's see if I can do that. This is the equation, right? Man, I wish you could make that big.
Oh, we can see it quite well, can't you, Rajan?
Reasonable. It's quite okay. I mean, it's okay.
Well, what I have for the video and all, it's big. Like, it's gonna look big.
Yeah, it's okay. Yeah, you can see that. You see K of Hodge and the K of, what is the first one? K of epsilon?
Yeah, and then n source I equal 1 sum to n source.
Yeah. This is the rho, which I consider to be a density function.
Okay.
Yeah. And the density is fed by sources, which are at center of spiral galaxies. And from that, you subtract sinks, which are elliptical galaxies.
Okay.
And these two things create a background against which the mass can now cause a negative number.
Oh. So K of Hodge is like a constant, or?
Well, these are the K's are constant, and part of the previous was to show you how I get these K's.
Okay.
See?
Uh-huh.
Because K here is 1, I put that as 1, and this is 2.7, because if you plot the, what can I do?
Is it like slope?
Say again?
Is it like a slope, value of a slope?
No. What I plotted here was the luminosity of the B band of sources versus sinks. And it looks like that as you go out from the galaxy. And that number right there is 2.718.
Oh, that's like an asymptotic value.
Yeah. Well, yeah, it looks like it. It looks just like it, but this is luminosity of sources divided by luminosity of sinks. So this is 1, and that becomes 2.718. That's the simulation, okay? But you subtract, and there's a cosine here,
Yeah.
which is what it's, and that's what fits in. This cosine term is what fits into
Something breaking
the
off.
linear antenna array, a series of cosines. And I was thinking that was like your Mexican hat.
Oh yeah.
This, right? This is a magnet.
Uh-huh.
See, a simple magnet. And
Yeah.
that's a Hodge. I mean, it's a our size, where this is a magnet, where there's North Pole and South Pole, and there's a magnetic field here.
Yeah.
That makes that, that makes that a photon.
Oh, so many Hodges. Okay.
Yeah, so a column of Hodge, which is a photon, and each one of these is producing a cosine field, which then creates the linear array function. You see? But if that's a photon, then that is a neutrino.
Oh.
Okay.
See, I'm assembling photons to make a neutrino.
Oh, okay.
Yeah.
Now, the thing about a photon is if it travels anywhere, you know, like that, this is zero surface area in this direction, and it's gravitational in this direction. See, so therefore, this thing can travel through space for very far, because there's no force on a two-dimensional object. So in the Hubble Deep Field, you can see those galaxies out there in the Hubble Deep Field very clearly, right? Because there's nothing to stop it. And by the way, it means there's no dampening. The Hubble Deep Field implies there's no dampening in this structure. Right? And if you go one more step, that's an electron.
Oh, okay.
You see how they cross? You can see a neutrino in, two neutrinos in there, and a couple of photons.
Yeah.
If you drop that, that is a very stable structure. I mean, that's why the structures exist, is because they become stable.
And there's a gluon. It's like gluon.
You can drop
inside?
this and it won't break apart.
I think you said it was an electron.
Well, no.
No
This
gluons.
is an electron.
Oh, just an electron, no gluons.
The gluon, yeah, the gluon would look like that. But a gluon, oh yeah, where can I do that?
The electrons don't have gluons, right?
No.
A gluon, here's a nucleus.
Ah, yes.
Oh,
Where can I put it? See, that's a nucleus where each of these little balls is a magnet, magnetic balls. And if you pull it apart, these are gluons.
Oh, okay. The gluon is holding them together.
Yeah, the gluon holds the quarks together in the quark confinement.
Yeah, and these are north. Yeah, these are north-south poles of magnets, you know, ball magnets. And that then would be similar to a gluon.
Yeah.
When you do that, that then is the connection to an electron. See, so that.
So there is a connection to electron.
To electrons. So you got nucleus connected to electrons, and that's the atomic structure. And the further these go out, the more energy there is, right? And what gets radiated is those things, photons. That's circular magnet. This is the spherical magnet. There's a disk magnet, you know. That's the idea.
Okay, I have a question though. or a couple, but when you were talking about, you have the model there of the photon, which is a pillar of Hodge, and you explained that it's two-dimensional in one direction and not in another. Which is, I wasn't able to make out which was the two-dimensional one and why.
See here, this is a flat surface.
Yes.
And this then, in the analogy with Hodge, would be a zero dimension in this direction. But they are held together. They are held together magnetically. That's why that thing has to be a magnet, because they're held together magnetically.
Yeah, I understand that part, but if there's multiple of them stacked, then how is it still two-dimensional? You get me?
Because these things are two-dimensional in this direction. In this direction, there's gravity in this direction, see? In this direction, they experience gravity as if it was the entire photon. So when this thing goes by a sun, this direction, it causes it to change direction. It's gravity.
Okay, so like, let's say you have along the length of it, the gravity is kind of working perpendicular to it, but then, is that right? Or and then
to the length, the actual dimension of the photon. And so gravity is attracting the photon along its axial dimension, but not according to the two-dimensional area here. Whereas in a neutron, in a neutron, you have only one direction that's zero dimension, and the other two directions have gravity attached. And of course, in this, you have gravity going in all three directions.
Yeah, I get that. A little bit more, I understand that. So, but why is your model for a gluon and a photon the same?
Because in a gluon, it's inside the nucleus.
Yeah, no, but you did, like, a gluon looks like a pillar of Hodge, exactly like a photon, yeah?
A pillar of Hodge, but you'll notice this thing being very short has zero energy, or you would measure zero energy. So this is not a free subject. This only exists inside of a nucleus.
Right. Can the shape of the Hodge change, or is it all constant?
I think to explain observations, you have to consider the Hodge as a rigid surface, like that is a rigid surface. At one time years ago, I thought that this thing might be a flexible film, like a piece of paper.
Yeah.
But it can't be. It's got to be solid.
It's very rigid.
Yeah.
It's like a rigid disc or something.
Yeah, I think so.
It's a disc magnet. That's what it is.
Right. Yeah, we can see that. That's interesting. So I was thinking about something there. I noticed that I think in the previous video you mentioned something about gravity being or the asymmetry in the magnetic field, because the north one was slightly stronger, I think, than the south one. Is that responsible for gravity being one directional?
Well, no. That thought was things like this, where in this direction you have gravity acting. In this direction you have gravity acting, but not in that direction.
Right.
See, if you're the gravity source, then that is attracted to you because that, you see, that is attracted to you, but that is not. And that's why when they look at this, the angle that light forms as it passes the sun is slightly different, because this has only one direction and all the Hodges are being attracted to the sun. Whereas in this case, not all the Hodges are being attracted to the sun. And the same with the electron. So when they do that calculation, that angle for the angle of light as changed by the sun, you can't use the two.
So the electron, there is a lot of.
Sorry, what was that?
The electron will be attracted in all three directions, but it varies.
Yeah, so the attraction is happening on the flat side?
On the flat side only. But yeah, on the flat side only. But you see, here's one flat side, there's another flat side, and these things are flat side too. So this will attract in all three directions, but it varies by direction. And this is where you get into the Stern-Gerlach experiment.
Okay.
One of the assumptions of the Stern-Gerlach experiment is that the electrons are coming in at an angle which is random. Not so. This has angle determined by this structure. See, it's going to travel one way or the other. And if you look at this structure, you'll see that there's a north pole. Well, on this one, there's a north pole here, a south pole going like that, another north pole going like that. There's four magnets here. There's four north-south pole structures. And that's what happens with the Stern-Gerlach experiment. If you take this thing and kind of suspend it and have it go through Stern-Gerlach, you'll see that it transfers like that. It spins like that. And that gives you the 720 degrees. But anyway, that's another subject.
Oh, so you can, wait a second, you can model a 723-degree rotation, like a spin 1/2, using that three-dimensional object there? Is that because
using this structure? In fact, that was one of the papers that I've written a while ago, is just suspending it and moving it through an inhomogeneous magnetic field, and you see the thing spin like that. And it takes 2 revolutions to get back to the original. But that depends very strongly on that this thing has an orientation as it's going through the magnetic field to begin with. The random orientation does not hold.
Yeah.
And of course, this thing also has a half spin, or that's to say, you calculate this in the Stern-Gerlach experiment as a half spin because there are 2 magnetic fields. You see, there's one here and one here. And because of that, this thing will have a half spin.
Okay. I'd have problem.
That's one of the papers.
So John, you say that there is gravity acting in the electron also, the gravitational field? The electron model?
Yeah.
There's gravity in all directions.
Model. In all directions, but is in all directions, but it varies slightly.
Oh. Because
there's different surface areas being presented, but it will attract in all directions.
Okay, that makes sense. I'm interested in the model here. Like, are they actually? You've kind of glued that together. I'm wondering, is it glued against the attractive forces there?
Oh, no. I did it so I can handle it, but these things come off. See, those are photons.
All right. Cool. Oh,
because this has to be a very stable structure, and it is. Magnetically, this is a very, very stable structure.
Okay.
That is to say, I can drop it and the thing stays together. It stays together until the magnets break. These are ceramic magnets.
Yeah, yeah. You don't want to drop magnets, obviously, because they're,
Well, not these, but these are ceramic. They will break if you drop them. But these magnets will break before the structure goes apart. Whereas, some other structures you could visualize, say, without those 2 photons in the end, see? If you drop that, that'll break.
Okay.
You know, they never come apart. Mainly because, if I can do it, mainly because this kind of a structure, see, although it's magnetically attracted, is weak.
Yeah, I see that.
And that being weak, yeah, and that being weak is why when you get to the atom, you have only one structure. You don't have this kind of structure coming from the atom. So you only have that structure because that is weak. And that means one proton gives you one electron being held together by a photon.
I get it. Yeah, that's interesting.
So you don't have you don't have electrons rotating, no angular momentum, and therefore there's no radiation from a stable atom.
All right. Yeah, you were talking about that last week. That's interesting.
Yeah.
And are the photons holding the electron together?
I missed that.
Oh, are the photons holding the electrons together?
Yes. I mean, these are different size magnets, but if that is a proton, then that's the photon, and that then is the electron.
Oh, so the photons are holding them together. The photons are removed, the electrons will become unstable.
No, I don't think so. It doesn't seem to me to be correct. I mean, like, you know, is it the photoelectric effect where you have, you know, if you bombard a load of electrons, they emit photons, but they can do it indefinitely.
Well,
there's an indefinite supply of photons within an electron.
This is inside the atom.
Oh, I know that.
If you move this out, if you move this electron out, it makes a bigger photon here.
Oh.
Yeah. And so if you then, in fact, another photon here, it could release an electron. But what you're doing is you're emitting a photon. See, now in the photoelectric effect, the slope of that line that you get is 1 Hodge, plus or minus 1 Hodge. Remember that the size of the photon is the number of Hodges. And so if you emit a photon, if you add one more photon to it, that's the H line, the Planck constant line that you get in photoelectric. So it's these photons that are holding the electrons to the nucleus of an atom. There's no angular momentum here. The photon is not rotating around, therefore it's not radiating energy. Very nice.
So you can produce free electrons by emitting a photon. You can create free electrons.
That's right. All you have to do is just move it so that you have a very long photon and get it away from that photon hole. This then is a free electron. And that's an electron in an atom.
Can you remove the electron in the nucleus? But gluon, right?
This can be, but notice that the gluon, that is to say that, is very short compared to a photon.
Oh, okay.
See, gluons don't have much energy relative to a photon. So when you remove this, it's going to become very susceptible to being latched on to anything, you know, including electron.
Okay.
Now, by the way, I guess you've noticed that there was a video of a double slit experiment offered on ResearchGate.
Yeah, I saw that.
Yeah, and you will notice that when he does that, if I can make it clear here, I'm not too sure I can do that. But when you look at his graph that he says he's measuring, what you see is a diffraction here.
Yeah.
But in between the diffraction, you see interference fringes, much like my graph, and you'll notice that that interference fringe does not go to ground, whereas the diffraction fringe does.
Okay.
Now that's a prediction of my model that is not found in other ideas of interference, because they all have the interference fringe going back to 0.
Yeah.
So I count that as a prediction, you see.
Okay, that's interesting. But,
Okay. We gotta figure out how to.
So, Christopher, you are saying about the quarks being, so how is the quarks then connected to Hodge?
oh yeah, that's a good question. What's the quark shape?
Well, the quark, I haven't got that yet. This is where you get to the electron, right? But then when you go to quarks, you've got to have something with more energy. So there's got to be quarks inside here, inside of the proteins. And you'll see that as you try to break this apart, you end up with all kinds of structures. Now, you'll also note that I said that the electron was a very stable structure.
Yeah.
Quarks are not stable.
Yeah, okay.
But I've been playing with the idea that electrons are held together by photons, and there might be another electron here. You see. So somehow or other that has to end up being a quark. You take them out like that.
But isn't there an issue that you can't remove a quark from the nucleus? Or you mean when you take them out, they become another nucleus or something?
When you crash a proton or neutron together, what you're doing is just pulling it apart. You see?
Yeah.
And somehow or other, and that has to do with an internal structure. If you look at this very carefully, you'll see that there's an internal structure here. The magnets are attracting each other, like two magnets do. So there is an internal structure in here. The question is what is it, when you pull it apart, you end up creating another structure, which then is attracted to everything. So it's not stable. And quarks are not stable. They're more stable than just, gluons, but they're not stable. So you got to have a structure.
The high energy with a fusion or fission type of thing.
Yeah, and if you
Neutron,
divide
neutron bombarding.
If you divide
bombarding a neutron or something.
Yeah, if you take a quark, it has to be made up of several electrons.
Oh, you were saying this
See,
before.
and it's a matter. Say again?
I think I heard you say that before, that a quark is. Oh no, I think you. Oh yeah, no, it was you were saying that an electron is made up of photons. So now you're saying that a quark is made up of electrons, possibly. Multiple.
And photons, and perhaps I don't know. See, I haven't got that far, because what you have to do to see what the structure is going to be is you got to drop that thing. And just dropping that, and seeing how it breaks apart. It does break apart if you drop it. These things are steel, so you can drop this. But the question is, the Hodge, as I say, is a flat surface on one side, two-dimensional, and these things are round. So when this thing breaks apart and you drop it, you get all kinds of stuff.
Okay.
Right? That would be a collision experiment. what I've got to do is to find flat metal object Hodge rather than these circular ones, and then drop those.
It's like a paper,
That's my
very thin disc. You are saying Hodge
What?
is a very thin disc.
Yeah.
Very
Yes.
thin, like a paper, like.
Or smaller.
What you could do there, John, is if you're looking for flat magnets, which I'm sure you know, you can find rare earth magnets inside speakers which are flat. I'm sure you could drop those.
Yeah, I know. What do I do with them?
Is it like
I found some that are flat and steel.
Sorry, what?
I just haven't dropped them yet. I found some magnets from Amazon that are flat and steel, which means I can drop them. I just haven't done the experiment yet. Got a lot of things to figure out.
Okay, and what do you hope to find out by dropping the magnets, though?
I hope to do a collision experiment like is done at CERN.
Oh.
How fast are they going to be traveling, do you think?
Well, I don't know. That's part of the experiment, is to figure that out.
Okay.
So what you do is, so you have them hit something. Question is, what do they hit? If they hit a flat surface, that's one action that can happen. If you hit a point, that's another type. Or if you hit another one, that two protons, that would be another one.
Yeah. Okay.
So there's some experimentation in that, you know.
Yeah, that's true. What about the? I was going to ask you. I think you mentioned something that the video you were going to show is going to explain how particles were definitely discrete particles and not waves. Is that correct?
That's correct.
How did you prove that, or how did you come to that conclusion?
Well, because there was no light going through the slit, and yet you had an interference pattern.
Oh yeah, but how do you get to that conclusion?
Well, it was demonstrated that if you block the light that's going through the slit, what you still get is an interference pattern.
Right, but why do you conclude from that there's no waves?
Because to get an interference pattern, you require a wave going through a slit. When the wave is, whatever light is, when it's going through the glass pane, right? There's no interference pattern generated there. Whoops, what am I doing? I just clicked off.
Sorry, what, John? Oh, sounds like there's a bit of feedback or something. Are you with us?
Oh,
I am now.
Oh, okay.
What happened there, John?
Something just clicked off.
Okay.
Turn camera on.
I think we were getting close to what we were talking about. You were. I was curious about why you use glass. Surely glass is transparent to light, so wouldn't it just go through the glass pane, or is
exactly. It goes through, but you'll notice the A is without a glass pane. The B result was a diffraction pattern that looked the same as without the glass.
Oh yeah, so the A result was the first experiment, was it?
Yeah, without glass. The B experiment was with glass but no slit. And that was a diffraction pattern from the first mask. The C was you put a slit between the glass plates and you got interference. You got to have the slit.
That's weird, isn't it?
You got to have the slit to have the interference pattern, but you don't need light to go through the slit.
Yeah.
So here we have a diffraction pattern to the side that goes through the glass as a diffraction pattern, but yet when it keeps on going,
deflection.
Yeah,
No,
when it keeps on going, yeah, when it keeps on going, you end up getting an interference pattern.
So the slit, it's deflecting, right? It's deflecting the light. It's deflecting the light. So when they deflect, they can interfere. They can intersect at some point and cause interference.
Well, the glass is not deflecting the light.
No, the slit, the slit.
Well, if it were a wave, the glass, the slit, should be deflecting the light in a diffraction pattern. See, that's how you get the wave explanation for the C version is that the wave goes through the slit and then that interferes with the other part of the diffraction pattern. All right. Because if you remember in the first part, I showed you what you get if you take two slits in opaque mask. You get a diffraction pattern out of that. You don't get an interference pattern, you get a diffraction pattern. You know, but then when you substitute glass for it with a slit, you end up getting interference. Which in the wave model, that should only occur if light is going through the slit. But in the C version, or in the D version, light is not going through a slit. And you still have interference as if that slit in the glass makes a difference.
But the glass.
Just ask a question about, or just a clarification on terms, because like if you were to shine a light through a slit and you get a diffraction pattern, like so let's say you have the double slit experiment, but you just shine it through one, you're going to get a diffraction pattern. You shine it through the other, block one off, you're going to get a diffraction pattern. Shine it through both, you get the interference pattern.
Right.
But the interference pattern is not the sum of the two diffraction patterns. Correct?
The interference pattern is the sum of the two diffraction patterns.
I don't think it is. I think if you look into the maths, you add both the diffraction patterns up, you do not get the interference pattern. That's as far as I understand it. If you look at Sudbury's book, he had that video by what's her name? Hassenfelder? Sabine?
Sabine.
Yeah, her video. I got some problems with that one.
I agree. I'm with you on that. But she does mention the fact that the two diffraction patterns do not create the interference pattern. But I thought her video was interesting, but I disagreed with her, and I didn't think she proved her point very well.
No. And one of the points she made was this business is in the interference pattern. She pointed that out as going to zero, which we saw in the video that Emmanuel put up, that it does go to zero.
Right. She did mention something about that. It was a bit strange, but I just felt, I mean, I thought her video was interesting, and she did explain something new that I didn't know about, or maybe I'd heard about it before, but the idea that the non-interference pattern is actually like a blob, and the two interference patterns, when put together, create the blob. So I thought that was kind of interesting. And also, there was a...
Yeah, but you see, that's wrong. That doesn't happen like that.
Okay. But she was maintaining that, yes, this is correct.
Well, but you notice she didn't show you any pictures of, photos taken. She was showing you little dots on her screen.
Yeah.
Theoretical.
I know, but I think she was saying that this was the result. Okay, let's say, but with the bigger problem, or the problem that I had with it, was that she seemed to... Do you know the way there's like these results and they're pretty weird, and then you get these physicists who like to come along, and I think what they like to do is kind of like rain on everyone's parade. They don't like people being astonished by things, especially if it leads to any kind of grander notion about how the universe could be affected by consciousness. But that also has to be tamped down a bit. You know, we can't have that. So then they come in, you know, and she didn't even explain this properly, but basically with the quantum erasure experiment, the light is hitting the detector after it hits the screen, but yet, based on which detectors are turned on, the result is different on the screen. So she didn't explain how it is that, you know, the quantum erasure part happens where it's backward compatible with time in a sense. She just kind of glossed over that. Oh, that's not important, or it's not happening. And I found that a bit odd. Did you notice that, or?
No, I agree with you. That's where one of the things that she was not describing an actual experiment.
Yeah.
At this point where she took a little dots on the screen and put that up. Her theory, you know, here's the dots on the screen.
Yeah.
Yeah.
Well, this is the thing about that particular experiment. It's a bit of a strange setup anyway, because like for a start, these photons or whatever these particles are using aren't actually going through any kind of slit. You know, there's no like screen with two lines in it. It's going through like a magneton kind of thing that is able to like split the beam this way or that way.
No, they do go through a slit.
Well, maybe I'm wrong.
Remember where these two beams are coming from in the actual experiment now is from a crystal, which for every photon that comes in, you get 2 photons out at half the energy each one.
But I think there, John, you're mixing up the beam splitter effect that allows for the entanglement and the actual splitting of the direction that the particle takes. Those are two different elements.
I don't think so. The experiment, what do you call it? Those quantum erasure experiments.
Yeah.
They come out of a slit or the slit apparatus, and they direct it into a crystal.
Yes.
And what the purpose of the crystal was, it takes an energetic photon and splits it into 2 photons of half energy each.
Okay.
See, and these go off in different directions, and that's where you start the quantum erasure from.
I agree with that. But what I'm saying is that a lot of these experiments that were done into the like the double slit experiments using subatomic particles, like if you think about it logically, you're not going to be able to create a slit small enough in a material for the particle to say, oh, I'll go this way or that way. And, you know, it would just be like, well, why would it choose either way? Why wouldn't it just run into the material? So as far as I know, it was explained to me in this way that in order to direct the photon in either direction, they actually use some sort of field. Like it's like a powerful magnetic thing, and it's however it's working, it either directs it this way or that way. So I'm wondering whether, based on what I heard, I mean, maybe that's wrong, but that sounds dubious kind of from the start. But the main point I'm trying to make is, and this is definitely, or well, you know, this is something I've heard, that when the particle goes through and hits the screen, it's just one dot. They have to repeat it over and over and over again in order to build up the interference pattern, which is what she was showing, that the interference pattern is made of individual dots. So it's multiple experiments that build that pattern up. So it is interesting that it would know which detector is on in order to show which diffraction pattern, and also that it knows it ahead of time because it hits the screen before it hits the detector. So she never really went into any of that. She kind of totally glossed it over and instead had something to do with, you know, her analogy was a captain of a ship who was aged 46. He gets on a boat and travels back, you know, and then she tried to tie it into the thing, and I was just like, by the end of it, I was like, I wasn't even sure where she said that the most important information was that there was no diffraction pattern or something. And I was like, sometimes I think in her videos, she just sweeps things under the rugs. Like, under the rug. She doesn't fully explain herself. Well, no, most of the time she's very good, but just that time, either I didn't understand her or she was doing a bit of a sleight of hand, I think, with the logic, but maybe I'm wrong.
Well, there's videos about the quantum eraser experiment on YouTube.
Yeah.
And perhaps you should pay attention to when they talk about the crystal that's doing the dividing of the photon.
Well,
that's before you do the eraser.
Oh no, I agree with that. But prior to the beam splitting effect is the actual so-called double slit that says the particle goes this way or that way. Then it hits the beam splitter, which creates the entanglement issue. You know.
No. That's not what they're saying. A beam splitter is a half silvered mirror.
Right.
I mean, you can look at it as just mirrors interspersed very closely together.
Yes. Okay. Fair enough.
That's not creating the entanglement. The entanglement is coming from the other beam. To have entanglement, theoretically, what you've got to have is coherence of the photons. And the way you get that is you take one photon and divide it into two.
Well, you would have.
The beam splitter thing will not give you an inference, or the beam splitter will not give you the inference that they're looking for.
Oh, I'm not saying that the beam splitter gives the interference. In fact, I hadn't really, in quantum erasure experiments, I hadn't really considered that it's an entanglement phenomenon, but it obviously is, because once you split one electron into or photon into two, then those two will obviously be entangled until such point that they are measured or whatever, or encounter something.
That's the point.
Right, but I wasn't suggesting that those two entangled photons go together to create the interference pattern. You know, I wasn't suggesting that. But I agree with the, I heard about the quantum erasure experiments years ago, and it always baffled and confused me. But I kind of agree with the conclusions. Like, if everything in the experiment is properly set up and the initial thing is correct, which is whether or not the actual double slit aspect of it is enough to actually generate, or, well, I mean, obviously it is. So, but getting to the point, I think that the distance thing and the time aspect, the actual erasure aspect, that it's erasing the past, I think that's convincing. And I find that this whole idea that her and Sean Carroll are talking about, that it's not convincing, to be a bit suspect, because their reasons for saying it isn't convincing aren't convincing. So that's where I have a problem. If they were like, this is wrong and this is the reason why, and it made sense, I'd be like, okay. But you also hear that a lot from people who just talk about the ordinary double slit experiment and say, oh yeah, there's nothing to do with consciousness. It's not about looking or not looking. But I mean, have they ever proven that? Because how would you know? How would you be able to rule consciousness out? It's only when you look like that. But maybe there is a reason why that's the case. Yeah?
I think, the question, what happens to slit, and I think something to do with, couple of things. One of them is, I think, has to do with chirality. So they may be left-handed, right-handed.
So no, they're left-handed, right-handed photons.
Yeah.
They're all the same.
Okay.
You can't have a photon and an antiphoton.
But the other aspect, what I am talking about, is the gradient and the vortex field.
Okay.
And they split up. The gradient and vortex field get split up. Then you can have, they will know, this vortex field will know automatically whether the other vortex field is there or not. So that's how they communicate.
Well, I mean, you have quantum entangled, like two entangled photons will react to one another.
Yeah, one of them have vortex like this. Another one has a different vortex.
No, they're all the same. I don't think there's right-handed or left-handed photons.
Not right-handed. The vortex. the type of vortex they have. Two
Yeah,
different
they
vortex.
can't be any different though. Photons are like bosons. They're supposedly they have no, they have no chirality. I could be wrong about that, but that was my understanding.
Yeah.
John,
But it may not be chiral. It may be like more like a mirror symmetry type of thing. It may not be completely.
chirality is mirror symmetry, isn't it?
Mirror means in the sense that the vortex, let's say, is a clockwise vortex. The other one is anti-clockwise. I'm just simplifying it, but it's more complicated than that. So if it is one is clockwise, other is anti-clockwise, it will always know that if there is a clockwise there, it will know there is an anti-clockwise somewhere else.
Okay, yeah, maybe there is, but apparently, I think from the point of view of what they say, there's no like anti-clockwise or clockwise photons. They're all somehow all the same. Weird, but that's it.
They may be one. I think they may not have measured this one because you have to know the vortex fields and you have to look at it in the correct way also. Suppose I'm looking at it like this, I will say both of them are same, but I look at it at a different angle, they are different.
No, but apparently there is no other angle. Like there's the same from every angle. That's the point.
So are they spherical? Are they all like spheres?
No, they're not spheres. Well, like according to I'm just talking about conventional physics here. They're supposed to be point particles, which does raise problems from the point of view of density, because they're going to be like, a certain amount of mass where energy packed into an infinitely small space is going to have consequences. Like,
I think there is more structure to the photon.
Apparently not. No, apparently from the point of view of physics, it's a point particle. Same with a photon.
But point has, like I pointed out, point has both gradient and vortex fields. A point has both.
Yeah, no, but I mean from the conventional point of view, it's meant to be dimensionless, like effectively. But
they're not sure. Some people say that photon has mass. Some people say photon has no mass.
Yeah, true.
So there is a and I have another question about the glass. When you put a glass, the glass can refract, right? Because it has a different refractive index.
Yeah.
So it can create that effect. Can it create that effect because of refraction through a glass?
No, because the A view and the B view were the same.
Oh.
Could you show us the A view again?
Without the glass, you saw a diffraction pattern. With the glass, but no slit, you still saw the diffraction pattern. Now,
so the refraction is very refraction doesn't affect.
The way you get an interference pattern is you have to have two slits. Now, in the normal double slit experiment, the slits are side by side. In the thing I just showed you, the slits are one behind the other.
But the slits don't they? When it go to a slit like this, it will deflect the photon this way, and if it goes to this reflecting, it can deflect the photon this way and can intersect each other.
Well, in the video, one of the things I showed you was what happens with two opaque mass. And you put that second slit in the second opaque mask over the center of the diffraction pattern from the first, and what you get is another diffraction pattern. You don't get an interference pattern that way. I mean, that was, that's a photo taken.